is a bijection. Matches up the elements on the left to the elements on the right in a one-to-one way. Each element is matched to exactly 1 on the other side. Here's another bijection. Given these two bijections, we can add them basically by running them in parallel. So I take a disjoint union of the sort of dark blue and the dark orange sets on the one side, and I take a disjoint union of the light blue and the light orange sets on the other side. And the bijection that I get goes between those disjoint unions, and it just runs F on one side and G on the other side. Okay, it just does a case analysis and runs the appropriate choice of F or G. Okay, so let me establish some ground rules for the rest of my talk. Types are the same as sets. I'm going to use those interchangeably. And also, everything is finite. Except for that, there's one little infinite thing at the end. But, and after my talk, we can all go back to our happy world where sets really can be infinite, and types and sets are definitely not the same thing, but just for now. Okay, so let's talk about subtraction. So here is that, here's a new bijection, H, and this one goes between two disjoint unions. And notice that it kind of mixes up the elements between the sides of the disjoint unions, right? So, there's an element in the blue set that goes down to an element in the orange set. So another way to say that is that this bijection definitely is not the sum of two bijections. Okay? So keep that in mind. So here's our old friend G, and I want to ask the question, since I can add bijections, can I subtract bijections? And it might not even be clear at this point that that makes any sense, but let me see if I can convince you that it ought to make sense. One thing we can say for sure is that the blue sets definitely have the same size, because H shows that those two disjoint unions have the same size. It's a bijection. G shows that those two orange sets have the same size, and so what's left, those blue sets must have the same size. So there must exist some bijection between those blue sets, but that's not good enough. I don't just want to know that one exists. I want an actual correspondence between elements that I can compute. So the name of the game is, can we come up with some kind of, well, I mean, we could just look at this and decide, oh, okay, let's just take that top element to, the middle one and this one to this one. But in general, of course, the elements might not have an order. There might be a lot of elements. So I want some kind of general principle that tells me how should I match these up. Just by looking at H and G, can I use the information contained in H and G to decide which things I should match up? I know one must exist. Can I find one? So I want you to turn to your neighbor and see if you can figure out how to do this. You have 60 seconds starting now. All right. So hopefully you figured it out. If not, that's okay. I'll tell you the answer in a minute. I'm going to give you a little bit of background first. Why would we care, or who cares about this? Where did this problem come from? So it really comes from combinatorics, the mathematics of counting things in fancy ways. And in combinatorics, it's not good enough to just to know that two sets are the same size. Mathematicians who do this, they want to know an actual bijection. And so this first arose in combinatorics in the context of, we know that these sets have the same size, and there's some smaller part that we know is the same size that we don't care about, and we want to find an actual bijection between what's left. But we don't know how to do that directly, but we have these other bijections. Can we somehow use them to come up with something? I think there actually can be applications in sort of computer science context. Talk to me if you're interested. It's sort of just speculation at this point. But so the first people to solve this problem, so Garcia and Milne and Gordon in the early 1980s. So basically for about 35 years, this has been sort of known within the combinatorics community. So let's play some ping pong. Here's our bijection H again. And remember, our goal is to come up with a way to match up the blue sets. So let's pick some element to start. And well, I guess maybe let's just follow H across to the other side. And I land in the other blue set. And that's exactly where I want to be. So maybe let's just say, fine, that looks good. Let's just match up those two. Done. Okay? And similarly, I can look at that next element. And if I follow H across, I guess I'm gesturing this way, but you're seeing it this way. Anyway, if I follow it across, it also lands in that other blue set, and that's where we want to be. So we'll say, okay, we're going to match those up as well. But what about this other one? So there's only one left. But again, remember, we're trying to come up with a general principle that tells us where it should go. So we want to figure out some reason why we should send it to that one place, the only place it could possibly go. So if we do the same thing and we follow H across, we end up in the wrong place, right? We don't end up in the blue set. But remember, we have some other data. We have that other bijection G that we haven't really used yet. So I'm going to sort of superimpose G here. Yeah, okay, you can see that. So I've written it G bar, indicating the inverse of G, to emphasize the fact that, as you can probably tell, we're going to follow G backwards. Okay, so we're going to sort of follow G inverse. And we can invert it because it's a bijection. So let's do that. We follow G backwards. Then we end up over on the other side again. H is defined everywhere on that entire side, so we can follow H across again. Still not where we want to be, so we'll follow G backwards again, and then we'll follow H one last time, and finally we land in the other blue set. Okay? And so indeed we're going to say, all right, victory. We bounced back and forth for a while until we ended up where we wanted to be, and we're going to say that those match up. I'll let you think about why this always works. You can read more about it in the paper. It's a nice little puzzle to convince yourself that this will always, it'll always terminate, and it always gives you something that is a bijection. Okay, so, oops. There we go. Okay, so this is in fact what we get, right? This is the output of doing this subtraction. We get this bijection. So, let's see some code to do this. So here's some code. Yuck. I know you were all thinking it. I appreciate that you didn't say anything about it, but I don't really like this, and there's a few reasons. So one is, it's got all these rights and lefts everywhere. We've got to like project into and out of some types, and it's just a lot of noise. It would be nice if that was sort of encapsulated for us. Another reason I don't like it is that notice, so this is just dealing with functions. So this is really only one direction of the bijection. We really need two directions for a bijection. And so, well, if we really wanted to do it, we'd have to maybe duplicate this code for the other direction, or maybe we could sort of use this as a subroutine, but we have to call it twice. And we'd really rather sort of do everything kind of at once, build the whole bijection in a higher level way. So let's get rid of that. There's going to be no code for the rest of my talk. There's lots of code in the paper, though. But the goal is just to use our visual intuition to see if we can understand how the solution works. And then, you could all go and write code once you understand the pictures. So Kenny and I, my co-author, our goal was, can we understand this in a higher level way, how to construct this principle that doesn't work on the level of following individual points around, and that does kind of both directions at the same time. Partly just for fun, partly to understand the math better, partly potentially as the foundation for doing a mechanized computer proof of this principle. So just as an aside, at the time we started, no one knew, we didn't know of anyone who had done a formal computer proof of this. So actually last year, Bjarke Gudmundsen in his master's thesis did this in Agda. It is a very heroic effort because it's, and I think he would agree with me, it was extremely low level and tedious. And so I think there's still room for, can we come up with a nice higher level proof, perhaps based on what I'm going to show you. Okay, so let's play some high level ping pong. All right, so going back to, here's our bijections H and G that we were looking at before. And the first thing I want to do, we were thinking about elements bouncing back and forth. I want to kind of unfold time out into a spatial dimension so that we can, I think it'll be easier to see what's happening. So there we go. So we're now looking at sort of a trace through time of what the elements are doing as they bounce back and forth. I've highlighted the paths of the elements we were looking at. So those two elements at the top are sort of those green edges that immediately end up in the other blue set. And the purple path traces what happened to that third element as it bounced back and forth, right? So we're seeing it through sort of multiple copies of the same set. And not only is this a nice way to visualize it, but it gives us an idea. Can we actually, sort of in a high-level compositional way, build that thing, that trace, and use that somehow to build the bijection that we want? So that's the idea. So what do we need to do that? So, of course, we need to encode bijections. We can just represent them as a pair of functions that are inverse, and we can compose them. There's an identity. We can flip them around. I'm sure you could all write that code. But looking back at this again, that's not quite enough, right? Because there's these gaps. And the thing is that G is only defined on those orange sets, and it's not defined on those blue sets. And so there's sort of this gap where things aren't defined. So we actually need to generalize to thinking about partial bijections, which are just like bijections, except they could be undefined in some places. So in the places where they are defined, if you go across, you definitely will come back to the same place, but there just may be some places where it's not defined, okay? And you can do all the same things with them that you can do with normal bijections. There's an identity, you can compose them, and so on. So this is just an example of composing these, and notice that the edges that end up in the composition are just the ones that correspond to a path that goes all the way through without, any interruption. So there's a few edges on the left side that end up getting dropped because they sort of run into an undefined thing, and it sort of disappears at that point. So if, the Kleisli monad for maybe means anything to you, that's what's going on here, right? That's how we would encode this as some functions from A to maybe B, and we just compose them in the usual way you would do that. Okay, so we've got our partial bijections. So now we have enough the tools to sort of build that trace. So instead of just having G inverse there, I want to think of it as the completely undefined partial bijection on the top, and then I add it in parallel with G inverse. And so that's what I'm using there. That's what accounts for that gap. Okay, and then I can compose all of these as usual. There's a few problems with this. So for one thing, how do we know when to stop? So how do I know not to do this? And there's actually a bigger problem, which is that even if we did know how many times to iterate this process, it doesn't even give us what we want. So 3 times, it turns out, is the right number, right? We figured that out. But actually, if you do this 3 times and you compose all of these as partial bijections, that's what you get, which is not what we wanted. And the reason is, right, that purple path is the only path that goes all the way through from the beginning to the end without ever hitting anything undefined in the middle, okay? Those 2 green things, right, they finish too soon. And as soon as they hit the blue set, then they stopped and they ran into this undefined gap, and we lost that information. It's not present in the final composed output anymore. So somehow we want to sort of keep track. As soon as something finishes, we want to remember that, so that, and then we keep iterating as other things are still like making their way through, and when they finish, then we'll remember that. And we sort of want to build up a picture of the whole bijection in that way. Okay, so here is sort of the key insight, that how we can do that in a high-level way, still using sort of high-level operations on bijections and partial bijections. So I'm going to iterate this process of making this trace, right? I start just with h. And if I just take h and I just look at what it does on those blue sets, right? There's those two edges that we saw that immediately make it over to the other blue set, and those are good. They're done. If I iterate once, then, well, it turns out there are no paths that make it all the way through there if I just look at the blue set. So it doesn't give us any additional information, right? Because that other element isn't done. It hasn't gotten there yet. If we iterate 3 times, right now we do get that one other edge that corresponds to that third element that makes it all the way through. And we could keep doing this, but it turns out if you keep doing this further, you won't get any new information. Everything will be completely undefined after that point. And it's a nice little exercise to convince yourself that all of these things on the right, those relationships between the blue sets that we get by iterating different numbers of times, they're all going to be sort of totally disjoint. Each one is going to give us a little bit of information about the bijection that we want. They're never going to conflict, and they're never going to overlap. I'm not going to give you a formal proof right now, but you can read in the paper why that's the case. And so here's the infinity I promised you. What we do is we do this, and we take an infinite lazy merge of those blue things, and that gives us exactly the bijection that we want. So there's a lot more in the paper. There is a lot of Haskell code that you can actually run. There is one important thing. If you look back at this previous slide, so you can see there's this triangle developing here. That should make you nervous. So it turns out if you do this in a naive way, it has quadratic performance. So we actually spend a bit of time at the end of the paper explaining how to get this to run in linear time without sacrificing the sort of high-level nature of the code. So we don't actually change the overall structure very much, but we tweak things, use some tricks, and get it to run in linear time. And you know, there's more details. We generalize things in a few different dimensions that I didn't talk about here. But so I encourage you to take a look at our paper. Thank you very much for listening.
Thanks, Brent. We have lots of questions. I guess I'll start with the most important one, which is there are different types of color blindness. How did you find a good scheme that works for as many people as possible?
That's a good question. Well, it's a website that I found where someone had done this, and I don't know exactly how they did it, but they had published a color palette, and they said, here's a set of 8 colors that are distinguishable to a large class of people with many different forms of color blindness. So I just used those colors. So I could I could post a link to it on the Slack or something like that if people want. So.
This was a question that was some way before the end. Does your assumption about finiteness imply that it's okay to identify sets and types?
Sure.
Yes.
They're related, yeah. I'm identifying sets and types just because I want to do combinatorics, and combinatorics we only care about finite sets, and then it all works out nicely just to say, well, types are sets, and of course, yeah. So I think it is related, yeah.
Have you proved this terminating in Agda? How hard would that be if you haven't?
Right, that's a very good question. So actually, right, I said one of our goals, our motivations was to try to formalize a proof of this in Agda. So we actually worked very hard on a proof in Agda, and it is not done. I think at this point, so using some of the insights that from Bjarke Gudmundsen's implementation, I'm pretty sure that you can take our development so far, and there's It just needs sort of some work to finish it out. I don't think there's anything fundamentally difficult there. It's a little tricky because usually the way people prove this terminates is they sort of invoke a proof by contradiction, and you can't really do that. So you have to have like sort of a constructive encoding of the pigeonhole principle and things like that. So there's some details to work out, but I think it can be done.
Is there a sense in which h minus g plus h equals h?
No. Yeah, so it's a funny kind of subtraction, right? It does not have the property that it's the inverse of addition. So I think it's the case that it's sort of, once you do it one time, it's sort of, if you kept iterating that, you would reach a fixed point. It would sort of be idempotent, but maybe there's some kind of adjunction there or something, I don't know.
Another question about subtraction. Does subtraction have a nice universal property?
Yeah, it probably does, but I haven't thought about it. Good question.
Does this work on infinite bijections?
Yes, if you're willing to wait infinitely long.
Someone says Beta says, I can't help thinking of comparing Git commits. Do you think there might be applications there?
Git commits? I confess I don't see the connection, but I'd be happy to chat with whoever asked that. So.
Beta.
Okay, great. Let's chat.
Instead of using partial bijections for G, why not complement it with an identity bijection on all other elements?
Say that again?
Instead of using partial bijections, why not complement it with an identity bijection? I think combine it with an identity bijection.
Oh, you mean, okay, I see. You mean like where we had those gaps? Oh, I guess you can't see that up there. To fill in the gaps with identity bijections. So if you put identity bijections in there, that doesn't give you what you want. You get the wrong thing out. You can stick in there, and we talk about this in the paper. Our first idea was to stick in the inverse of the thing you've already built so far, so that things kind of recycle back to the beginning and then can keep going while you're waiting for the other things to finish. It turns out this is a horrible, terrible, no good, very bad idea. It's like, exponential, and anyway, but.
Someone asks whether you can generalize to division somehow.
Division?
Having a bijection between 2 times A and 2 times B, constructed a bijection A times B.
Well, you can certainly think about, so multiplication makes sense on bijections, or you end up with a bijection between Cartesian products, but I don't know. It'd be interesting to see if division makes sense. I'm not sure. There's some really cool papers actually on doing division when you're dividing by a constant. So if you're not dividing by sort of an arbitrary bijection, but by, I can't think of the name of it off the top of my head, but some very cool work on that.
There's a question here, I'm not sure I understand, but maybe you do. Would this work for anything less than or equal to omega as an ordinal?
Anything less than or equal to omega as an ordinal.
Could you explain what the question means first?
Well, I mean, omega is sort of the first infinite ordinal, right? So, well, less than, certainly, that means finite, but equal to, I mean, again, it does work on infinite things. You just, the ping-ponging process may go for an infinite amount of time. And so it's, yeah.
Okay. I think that's it, so thank you very much.